Hello everybody. Welcome to my talk on stability of positive linear discrete time systems. My name is Andrii Mironchenko and this is a joint work with Glück. In this talk we consider discrete time systems of this form where T is a linear bounded operator on a Banach space X. Such a system is called exponentially stable if there are two positive numbers a and m, where a is less than 1, such that the norm of the trajectory can be upper bounded by such an expression for all initial conditions x and all times k. The study of exponential stability for linear discrete time systems is a classic topic, and there are many criteria for such a property. Let me recall the most basic of them, namely that this system is exponentially stable if and only if the spectral radius of the operator T is less than 1. There are many other criteria for this property, and you can find them summarized in the survey part of this paper by Jochen and me. At the same time, in many applications, the operator T is not only linear but also a positive operator. To see this, consider the following problem. Assume that we have a coupled system with finite or infinitely many subsystems, all of which are stable. And the question will be under which conditions the interconnection of such systems will be stable as well. One of the ways how one can approach this problem is a small gain theory. Within this theory, one assumes that the influence of subsystem with the index j over the subsystem with the index I can be associated with some positive number gamma ij, which is called gain. The larger is this gain, the more influence induces subsystem j over the subsystem I. Now we collect all these gains gamma ij into a gain matrix, which defines gain operator gamma, which acts on some sequence space LP. And it turns out that if the spectral radius of gamma is less than 1, well, which means that if this operator generates an exponentially stable linear system, linear discrete time system, then the whole network of stable systems will be stable as well. And this simplifies the stability analysis of such networks essentially. What is important for us? That in all such applications, in all small gain theorems, this gain operator gamma is always a positive operator, which poses a problem. How we can use positivity of a linear operator to derive more powerful criteria for uniform exponential stability of the corresponding discrete time systems? Well, quite surprisingly, it turns out that although there are really dozens of criteria for exponential stability of linear discrete time systems, if we add positivity in play, then all of them cannot be simplified significantly. So the problem basically stays as complex as it was. We cannot use positivity there. Therefore, what we would like to do is to derive new criteria for exponential stability of discrete time systems that can fully use the positivity of a linear operator. And that's what we do in this talk. But before we do that, we need some preliminaries. A pair consisting of a linear Banach space, of a real Banach space X and its subspace X plus is called an ordered Banach space if X plus is a non-empty closed set satisfying these two conditions. The first of them tells that linear combination of any two elements from a positive cone, well, of this set X plus is again in this set if these scalar coefficients are negative. And if we intersect X plus with minus X plus, then what we get is just a zero vector. If X plus satisfies all these conditions, then it is called a positive cone. And having such a cone, we can introduce a partial order on the Banach space X. Namely, for all vectors xy in X, we say that X is less or equal than Y if y minus x lies in the positive cone. And it is easy to see that all the axioms of partial order are fulfilled with this relation. It turns out that in many applications, the cones have additional nice properties. Therefore, it makes sense to introduce some systematics. A cone x plus in an ordered Banach space X we call total if such a set consisting of the differences between the elements of the positive cone is dense in X. If this set is not only dense in X but actually equals to X, then we call a cone x plus generating. If there are some points in the topological interior of a positive cone, then we say that cone has an empty interior. And finally, we call a cone x plus normal if there is some positive number c, such that for all elements x and y from the positive cone, if x is less equal than y, then it holds that the norm of x is also less equal than the norm of y, but multiplied by this c. So this is called normality. It is well known that if the cone has non-empty interior, then it is generating. And if it is generating, then just by definition it is total. Well, finally, if we have an ordered Banach space X, then a mapping from X to X is called positive if it maps positive cone into positive cone. Let me give some examples. The simplest ordered Banach spaces are ordered Euclidean spaces. In this case, as X, we take the space Rn of n-dimensional real vectors, and as a positive cone, we take just non-negative vectors in Rn. With this choice, this will be an ordered Banach space, and the corresponding order is just the pointwise order. Similarly, we can define ordered sequence spaces. In this case, we take as the Banach space X the space LP, consisting of all real sequences with finite LP norm, where LP norm is defined in this way for finite P and by this expression for infinite P. So with this choice of a norm, X is a Banach space. If in addition we choose a positive cone as all elements of LP with non-negative components, then what we obtain is an ordered Banach space LP, where the corresponding cone is generating a normal. If P equals to infinity, then in addition, the interior of a positive cone is non-empty. Well, these examples basically show that a cone, it is natural to assume that the cone is generating a normal. In many applications, this will be satisfied. But at the same time, it is not always reasonable to assume that we have a non-empty interior, because already for sequence spaces in infinite dimensional space, well, let's say for infinite sequences, this is valid only if P equals to infinity. And it is not so if P is finite. Okay, so having provided these examples, we can proceed to our main task, namely to characterizations of exponential stability for linear discrete time systems. As a motivation, let us consider how these criteria look like for ordered Euclidean spaces, where it is a well-known result. So now we take X as Rn and our positive cone as Rn plus, and we take T a positive operator in this ordered Banach space. It can be then represented by a non-negative matrix. And for such T, the following statements are equivalent. The spectral radius of T is less than 1 if and only if such a small gain condition holds, which tells us that operator T does not increase on any vector X from the positive cone, which is non-zero. And such a condition is again equivalent to existence of a point of strict decay, namely of a vector in the topological interior of a positive cone, such that T decays in each component of this vector with some uniform rate lambda. This result is well known, but let me recall you the proof of one implication, how 2 implies 1. Assume that 2 holds, and assume that the condition 1 doesn't hold. So this means that the spectral radius of a linear operator is greater or equal than 1. Invoking Perron-Frobenius theorem, we know that R of t is an eigenvalue of an operator t, and moreover, the corresponding eigenvector is positive. And applying t to this eigenvector, we obtain that tx equals to R of t times x. And since the spectral radius is greater or equal than 1, by our assumption, then tx greater or equal than x. And we obtain a contradiction to the small gain condition. So the proof is extremely easy, but it is easy because we have Perron-Frobenius theorem. Okay, so after such conference, what we would like after this result, we would like to extend it to the infinite dimensional case. Well, let us make some reflections on this result. Well, first of all, here in the third item, we say that this is equivalent to existence of a point in the interior of a positive cone. For finite dimensional systems, this is true, but for infinite dimension operators in infinite dimensional spaces, it is not necessarily true, just because the interior can be empty. Also, we have seen that in order to prove from 2 the condition 1 holds, we have used for finite dimensional case the Perron-Frobenius theorem. There is indeed an extension of this result to general ordered Banach spaces, which is called Krein-Rootman theorem. However, this theorem requires that the operator T is quasi-compact, which is a rather strong assumption, and for example, it is not reasonable to assume this quasi-compactness for applications of the small gain theory. So this assumption is too strong, and this means that we do not have a proof that 2 implies 1. In fact, it is even worse, because the condition 2 does not imply 1. And to see this, consider such a discrete-time system. We consider it in a Banach space L infinity with a standard positive cone, which is normal and even has non-empty interior, so very nice properties. And operator R is just a right shift on X. So it takes the sequence, shifts by 1 component, and adds 0 to the beginning. Now, one can see that the small gain condition holds for this operator, or even if we take 2 times R. But at the same time, the trajectories for this discrete time system diverge exponentially to infinity in case for all initial conditions which are non-zero. Well, this means that this small gain condition is far too weak to ensure that the spectral radius of a linear positive operator is less than 1. Okay. Well, so basically now we need somehow to fix this condition. And let us think on that. Well, first of all, this small gain condition is clearly equivalent to this one. We just take x and put it to this direction, just subtract x from both sides, right? And now if we have subtracted it, now this condition is clearly equivalent to the fact that this guy, this vector, tx minus x, has positive distance to the cone x plus, right? So for all x from x plus, which is non-zero, such a distance is positive. But at the same time, it may happen that the infimum of these distances where we take norm of x equal to 1, so for all x from the positive cone with the same norm, that this infimum is 0. And this is rather bad, because this means that we have some lack of uniformity in this condition. And it turns out that this is precisely the reason why the equivalence between this condition and the exponential stability of the discrete time system fails. And therefore, we introduce the following condition, the so-called uniform small gain condition, which tells that this number, which we can call eta, which is the infimum of these guys, over all elements of a positive cone with norm 1 is positive. Well, this is the same as to say that for all x from x plus, this distance is greater or equal than eta times norm of x for some positive. And we will use it, we usually use this uniform small gain condition in this form. For those of you who have training in nonlinear small gain theory, I can say that we have an extension of this condition to nonlinear discrete time systems. Then instead of this term, we need to put here some k infinity function of the norm of x. And in this generalized nonlinear form, it is very useful to analysis of stability of nonlinear discrete time systems. But that's all for nonlinear systems. So here, for linear ones, it is sufficient to have such a bound from below. Well, now, having understood what should be the right small gain condition, we can formulate our main result. Namely, let we have an ordered Banach space X with a generating a normal cone, which is a normal assumption as we know. And now let T be a linear positive operator on this space X. Then the spectral radius of T is less than 1 if and only if T satisfies the uniform small gain condition. I will not present here the proof, but you can find it in this paper, which has recently appeared in Positivity. And also we show not only this criterion, but we have actually 8 or 9 criteria for exponential stability of the positive linear operator T, which simplifies the verification of these conditions essentially. Now let us proceed to a more special case. Now I would like to assume that the cone X plus is not only normal and generating, but it is normal and has non-empty interior. Well, you can think about L infinity space. And again, we assume that T is a positive operator. Now, we can show that this, what we can call spectral small gain condition, is equivalent to the existence of a point of strict decay, namely of a vector in the interior of X plus, such that Tz is less or equal than lambda z, for some lambda less than 1. Okay. Furthermore, actually, for applications, it is important not only to have such an equivalence, but also to find an explicit expression for this vector z, for this point of strict decay. And we can not only show these equivalences, but we can actually construct this point in a very convenient way. Okay? So how do we do it? Well, we start with any point from the interior of X plus. Let's say if X plus is X is L infinity, then we can take just vector of all ones. Now we pick any lambda between A and 1. Well, just recall, A was here, let's say a decay rate, let's say of our operator T, and it must be less than 1, so therefore we can find some lambda between A and 1. And now we consider the following vector Zn, defined by this sum, where n can be either finite or infinite. Let us analyze the properties of this vector. Yeah, before that, let me just mention that if n is infinity, then this vector is this sum, which is precisely the action of the resolvent of t onto the operator y. Okay, so now let us analyze the properties of Zn. First of all, since t is a positive operator, all these guys in this sum are positive, well, at least non-negative. So this means that this vector is greater or equal than the zeroth element of this sum. And zeroth element is precisely y over lambda. Since y is in the interior of x plus, then also Zn is the interior of a positive cone, which is good. Now we need to verify that t of Zn decays at this vector. That t decays at this vector. Okay, to see this, we just take it and subtract and add lambda identity. We apply all these three guys to the vector Zn, and we have this. Afterwards, while t of Zn, we just apply bilinearity t we apply to each guy in this sum, and we have that t of Zn, after some straightforward computations, is equal to this term. Now, since this guy tends to 0 when n goes to infinity, and since y is in the interior of a positive cone, then we can always find a finite number n such that this term is less or equal than 0. And therefore, this guy is less or equal than lambda times Zn, right? So overall, Zn is a point of strict decay for an operator t. As I have told, the explicit expression is very important for, in particular, for the small game theory, because it helps to construct Lyapunov functions for complex networks if we have Lyapunov functions for subnetworks. And just note that this construction is new even for finite-dimensional discrete-time systems. Now let me go for another special case. Namely, now we do not want to make additional assumptions on a positive cone, but rather we would like to make additional assumptions on our operator t. So now we assume that X is an ordered Banach space with just total cone. We even don't need normality, and we do not need that it is generated. And now let T be a positive operator, and in addition, let it be quasi-compact. Then the spectral radius of T is less than 1 if and only if the classical finite-dimensional small gain condition holds. And as you can imagine, the proof will be similar to that of finite-dimensional case, and it follows by Crane-Rootman theorem. But in particular, we can say actually much more about that and give more precise characterizations for this property, which go beyond the finite-dimensional technique. So just see the journal version of the paper for that. So let me go now we go to conclusions. So what we wanted to do is to characterize the condition that the spectral radius is less than 1 for positive linear operators in ordered Banach spaces. We have shown that if the cone is normal and generating, which holds for many of the important in applications ordered Banach spaces, and under this condition the spectral radius is less than 1 if and only if the uniform small gain condition holds. If X plus is normal and has interior points, then in addition, R of t is less than 1 if and only if there is a point of strict decay for an operator t. And if t is quasi-compact, then the exponential stability of a discrete-time system generated by t is equivalent to the classical small gain condition. But furthermore, each of these cases will have many more additional characterizations for this property. And also in the journal version, you can find a survey of the classical results for exponential stability of discrete time systems in Banach spaces that do not necessarily have an order, which makes it possible to put our results very precisely into the state of the art of the theory of stability for linear discrete time systems. So you can find all these results in this journal version of the paper, which was published in Positivity in the last year. But also let me say that we have something more than only that. Namely, some of the results which I have presented today were extended for operators T which are not necessarily linear, but which are homogeneous and subadditive. For example, the maximum operators which give the maximum of all components of an infinite sequence. They are of this kind. Also, some of the results can be extended even to generic nonlinear case. And furthermore, we can apply all these results to analysis of infinite networks of nonlinear continuous time systems. For example, here we have used it using these homogeneous results. In this paper, we have obtained the general nonlinear small-gate theorems for stability of infinite interconnections of nonlinear infinite-dimensional systems. Here you can find the Lyapunov-based small-game theorem for infinite networks of nonlinear ODEs, and here there is a linear result, which is based on the criteria from which I have just presented in this talk. Finally, what is also interesting is that the results which I have presented today have some sort of extensions, or if you say the counterparts in the continuous time setting. Namely, we can consider the systems of the form x dot equals ax, where A generates a positive C0 semigroup. And for such systems, we can characterize the negativity of the spectral bound of the operator A. And this will be done in this paper, which is going to be submitted in this year. At this point, I would like to close my presentations. Thanks a lot for your attention, and I'm looking forward to your questions.